Hello and welcome to this brief presentation of our work, titled Have We Seen It All? Scene Graph-Aware Deep Point Cloud Compression. To begin with, why compress point clouds? Well, modern robotic systems increasingly rely on 3D LiDAR scans for essential tasks such as localization and mapping, autonomous navigation, and semantic scene understanding. At the same time, larger-scale missions and multi-agent systems are following a growing trend towards cloud offloading and edge computing to handle intensive computations. However, transmitting these extensive, unstructured LiDAR scans introduces significant bandwidth constraints. For example, transmitting raw point cloud data at 2 megabyte per frame at 10 Hz requires bandwidth exceeding 160 megabits per second, posing severe challenges under limited or intermittent connectivity. Traditional compression methods struggle at high compression rates, leading to exponentially increasing reconstruction errors and losing critical geometric details necessary for effective robotic perception, as illustrated in this compressed example. These losses in fidelity can severely hinder subsequent robotic tasks, such as multi-agent pose graph optimization or multi-robot map merging, reducing overall mission effectiveness and reliability. Let's have a quick look into the pipeline of the proposed framework. We start with a semantic point cloud as the input. Then we generate a semantic scene graph, SSG, which organizes the scene into meaningful layers: terrain, infrastructure, objects, and agents. These layers form a hierarchical structure where nodes represent semantic components and edges capture spatial and hierarchical relationships, such as cars linked to roads, signs connected to sidewalks, or pedestrians associated with the sidewalk. Next, we perform patch extraction, where each distinct object, infrastructure element, or agent that forms a node is directly converted into a patch. However, terrain nodes, which typically cover larger areas, are further subdivided into smaller uniform grid patches to efficiently manage their spatial extent and detail. Each patch is then encoded by one of 4 semantic-aware transformer-based encoders, each corresponding to a specific layer. These layer-specific encoders condition their representations on the semantic label, helping them capture both semantic and geometric features tailored to each layer's characteristics. These latent vectors, along with the semantic scene graph, are transmitted, drastically reducing bandwidth requirements compared to raw point cloud transmission. On the receiving side, we decode the patches conditioned explicitly on the transmitted semantic scene graph's attributes, such as node bounding boxes, reconstructing high-fidelity geometry from the latent vectors. Finally, we utilize the semantic scene graph to retrieve spatial relationships, enabling accurate reconstruction of scene context, crucial for downstream robotics tasks. Our method compresses a raw LiDAR scan from 2.1 megabyte down to just 45.4 kilobytes, achieving approximately 98% compression rate, while maintaining strong geometric fidelity at approximately 2 bits per point. Here is a visual demonstration of our compression in action. On the left, you see the raw LiDAR scans, and on the right, the decompressed scans at around 2.5 bits per point. Notice how the semantic scene graph captures the semantic and hierarchical structure, while the cumulative map is being reconstructed in the background. Even at a 98% reduction in data size, our compressed results closely resemble the original scans, preserving quality essential for downstream robotics tasks. We continue then to validate in practical downstream robotics tasks. To validate our compression method quantitatively, we first consider a multi-robot localization scenario. Using SemanticKITTI sequences 00 and 07, we simulated 2 robotic agents exchanging compressed point clouds. Intercession loop closures were identified and geometrically verified using generalized ICP, GICP, by aligning raw scans from one sequence with the decompressed scans from another. Successfully verified loops were then integrated into a pose graph and optimized using GSAM. Our compressed scans achieved localization accuracy close to the raw scans, despite the significant reduction in bandwidth. In contrast, traditional compression methods like MPEG and Draco experienced numerous rejected loop closures due to poor geometric reconstruction, causing GICP to frequently fail convergence. In addition, the transmission bandwidth was drastically reduced from around 168 megabits per second for raw scans to approximately 3.5 megabits per second with our method, maintaining reliable performance even at nearly 98% compression. Next, we examine our method's effectiveness in another essential robotics task, multi-robot map merging. In this experiment, we merged 2 independently built maps, one from the decompressed scans and the other from raw scans, again utilizing sequences 0 and 07 from SemanticKITTI. Alignment was performed using KissMatcher. Our compression method maintains sufficient geometric fidelity, allowing KissMatcher to successfully identify correspondences between the raw and decompressed maps. In contrast, traditional compression approaches fail to retain this fidelity, resulting in unsuccessful map alignments. In summary, our compressed representations not only reduce bandwidth significantly, but also retain critical scene information, facilitating efficient multi-agent robotic collaboration. Thank you for watching. For further details, please refer to our article.